We are live again. And what are we doing? Well, we have reading week coming up next week, so that means no classes, so please don't come to class anymore. So you get a week of vacation, and then you get to enjoy a wonderful little midterm on the Tuesday following the reading week, which is, I don't know if that's good or bad for you, but I was thinking that you'd have the extra time to study. So that's why the midterm's after the reading week. And it's going to cover everything up to what we finished today, which we will finish in about 40 minutes. And then we'll do a little bit of like a midterm review, which is really just like a summary of kind of what we covered since midterm 1, which is really going to be the focus of midterm 2. There should be almost no questions that are like similar to midterm 1, other than the fact that you probably need to kind of know how to do all this stuff from midterm 1 to be able to solve the questions in midterm 2. As you have already seen, you kind of need to know the concepts. And for the midterm review, when we get to it, I have put it on the website, so you can just download it if you want. It's like the iPad Note version. Okay. Let us get back into what we were doing. And what we were doing was we were trying to learn, well, maybe I should use the word learn carefully, but we were trying to understand how to estimate PDFs or PMFs. And motivated, why did we care about estimating these? Well, we were motivated by what we saw in the maximum likelihood notes. So let me just bring you back to there, which was that really the predictor, the model that is the best possible model you could imagine outputting, turns out to be the expected value of your label given the feature. And that's just, if you write it out, it's an integral for the regression setting. And so all we need is this conditional PDF. And if we have that, we are good to go, because then we can calculate this integral. And even better, this integral is just like the expected value. So if our corresponding distribution was nice, that maybe the expected value is just a parameter. Well, then if we had learned that parameter to begin with, then we already know what the value of this was, which we had seen before for MLE. In MLE, we saw, we learned the PDF of a Gaussian, which means we just learn the parameter describing its mean, its expected value. Then we need to plug it back in here. And this was a really simple calculation because, of course, the expected value was just the parameter we just had learned. And that parameter turned out to match the solution to empirical risk minimization under appropriate assumptions on the distribution and things like that. And okay, that was the story of MLE. And that's why we care about estimating this thing. And MLE just, it estimated it through saying, well, I have this data set. And I don't know what the distribution is, but for different distributions, the probability of getting the data set may differ. And so I can define what is called a likelihood function. So this was the likelihood. We've labeled it below, you'll see in a moment, but I'm going to label it again. It's called your likelihood. And this is to be thought of as a function of your parameters, W for a fixed data set, and it tells you kind of what is the likelihood that these parameters that describe the distribution are kind of the correct distribution. And yeah, that was this maximum likelihood estimation. And in this maximum a posteriori, which is going to be a different method of estimating distributions or PDFs and PMFs, it views it slightly differently, which it says like, okay, maybe my parameters themselves are like some random variable, which I have some knowledge of what, maybe the parameters, what values they could be. And maybe I have some prior knowledge that maybe those parameters, like for people's height, is a positive number. And it's a positive number maybe around, my guess is 160 centimeters or something. And so I'd like to be able to kind of maybe encode that information and kind of skew my estimation by this prior knowledge I have. And this is one way to think about this maximum a posteriori. And why this view is equivalent to this maximization is because of the following. So maximum a posteriori parameter is defined as, or I'm just going to call it map, the map parameter, is defined as the parameter, right, that maximizes the probability of that parameter given the data set. And we can now, since we treat this as a random variable, we can use Bayes' rule, which just here to here gives you an equation as follows. And we want to maximize this quantity. And since the denominator has nothing to do with the parameter, it's just a constant scaling a function. It's not going to change the maximizer. So that can go away. And we end up with an expression like this, which is that the map estimate is just the parameter that maximizes the likelihood, which we have already seen before, times the prior, which is our kind of our prior knowledge, our assumptions kind of on what the parameter might look like. And another thing I wanted to mention is this term over here in map. This is called your posterior in statistics. And I guess the word kind of makes sense. It's like you had some prior knowledge, you got some data, you updated your prior knowledge to this posterior distribution of W. Right? So you have prior, now you have posterior on W conditioned on the data you got. Okay. And yeah, that was all you really needed to know, because afterwards it's just a matter of solving an optimization problem. Okay. And then all that was left to do was just to work this out for like a simple kind of case that's not in the machine learning setting, and then map it back to machine learning and see what happens. And so let's continue working through the example we were on last time. So the example is with people's height. So you have some random variable zi describing the height of people. And this is the height of the ith perso, apparently. Forgot the n. That's interesting. So it describes the height of a person. There's some true mean, which describes the height of people. Turns out that it's normally distributed. We talked about how the variance we assume is 1. That's kind of a simplifying assumption. You could make that a variable and work things out as well, but we will not do that. Maybe you do that on your assignment. I can't remember. Maybe you'll do it on your midterm. I haven't made it yet, so we'll see. Okay, but you can imagine the procedure is going to be the same story. Okay, what that tells you is that the PDF of Z follows the following structure for the true parameter mu star. Notice this beautiful thing, though I've repeated many times, is that having functions such as this PDF is just a function that is described by a single parameter or like multiple parameters is really nice, because it's just like this mu star tells you exactly what that's all you need to know. Then you know that I'm using this type of function. I just plug in mu star and I know exactly what it is. So then all these procedures of searching over functions and so on just reduces to searching over a single number or potentially multiple parameters, which is multiple numbers. Okay, anyways, this so far is the same as MLE. This exactly was the same. The new thing for this map stuff is that we introduced this kind of prior knowledge. And this is just our assumption. We assume, or we have this prior knowledge that, well, I think this mu star parameter, I think it's going to be distributed normally for some reason with expected value, let's say 160 for people's height, and with some variance. And this, we should really pick a number, but we're going to keep it as a variable because we'll see that the choice of this will kind of differ. Well, clearly, the larger this is, the less certain we are, because it says we're very far from 160. And the smaller this is, it basically means we have like absolute certainty. Oh, that's a terrible normal distribution, but we have absolute certainty around 160 if there's 0 variance. Okay, and yeah, it has a PDF. That's what that means. And now we're just left to solve this optimization problem with these two functions that we now know what they are because we have defined things above. Okay, so let's just go ahead and work this out. Yeah. Sorry, I'm just finding the notes so I don't make a mistake. Okay. How does this procedure work? Well, we've seen this before. Okay. So first thing is we want to expand the likelihood to this product of things because, well, if you remember, the data is IID, right? These things are IID. And if you remember, you can rewrite this thing as a product over the data points of the same PDF for each Z. So it's like the product I equal 1 to n of P of this P of Zi conditioned on the corresponding mu, right? Okay. And next thing is same story. We're going to want to take derivatives. Taking derivatives of products is hard. So let's take the logarithm to make this the sum. This is trying to make this into the negative log likelihood. So let's just do that in one step. We're going to take the negative and change it to minimization, and then take the log and change it to a sum. So first thing, change the max to a min, then change it to minimizing, or sorry, change it to the negative. And now remove the product, take the log of the whole product, change the log of a product to the sum of logs, and we have this. And then we remember that inside here you have the log of two products. We can simplify this further by breaking it up into a sum of logs inside the big sum. Plus log. Beautiful. Now we can plug things in, right? And if we plug things in, it's going to get ugly, because what that means is plug this in and plug this in. And given how big I'm writing in here, there's no chance that's going to fit in the next line. But the good thing is, if you just look a little carefully, this quantity here is exactly the negative log likelihood we've seen before, right? This is the thing we solved. We solved this problem exactly when we did maximum likelihood estimation. And we just solved exactly this. The thing that's new is this log here, right? And the point is that we had expanded this out before. And so I'm just going to save us some time and rewrite this quantity inside here after a couple steps that we already did in the past. Okay. And so what's going to happen here is that, okay, let me move this up a little bit because it's going to cut it off otherwise. This quantity in here, this log of this Gaussian PDF, well, I mean, we also saw it before. It's like the log of this thing cancels out because just the constant doesn't matter for the maximization. The log of the exponential cancels out. The negative cancels out the negative outside of the sum. And then you end up with just this over 2. Yeah, and we're going to move, because those negative cancel out, we're just going to move this negative inside here. And this negative, that's just the negative being applied inside, and we end up with the following. Okay, let me just, yeah, we'll do it in 2 steps. Okay, so you have this Zi minus mu squared over 2. Okay, and then you notice, oh, this sum only applies to the first term. So let's just do that in this step as well. Sum only applies to the first term, and you get this negative log p of mu out here. Okay, great. And now I'm going to just expand this out. Okay, so we still are minimizing this whole quantity here. And now this is simplified. We can take its derivative. We've done it before. We're going to do that. This guy here, I'm just going to separately expand it out to see what it looks like. So in blue, I'm just going to do log of p of mu equals to the log of, I just take this equation and plug it in. And just then we observe again, you should learn this trick by now, the log of 2 products is going to be the sum of the logs. And then nicely, this log cancels with this exponential. Oh. Okay. So log cancels with the exponential, and we are just left with this. Right. Okay, and all we were doing was just expanding out this quantity. This was just the only new thing compared to maximum likelihood. And now that we've expanded it out, I'm just going to plug it in to there. So now going back to this black equations, continuing, we end up with this, and now this quantity is simply replaced with this. And remember, there was a negative in front, and we only calculated the positive version. So we're going to expand the negative into all the terms here. So negative this, and then it goes into here, and you get positive this. Okay. And so we're minimizing this entire thing. And maybe I can just make that very clear. This whole thing is being minimized with respect to mu. And okay, we have a function here of mu, but if we look closely, this is a function of mu. This is a function of mu. That's the new part. And this is just a constant. And as we have seen, a constant shift of a function is not going to change the minimizer. So this goes away. And we're almost there, because now we are left with this. And we're just going to solve for the closed form solution for this. We're just going to take the derivatives and set it to 0. Okay. And so taking the derivative, I'm going to call this function g of mu. I want to minimize a function of mu, right? Minimize with, how am I going to do that? Set the derivative to 0. So let's do that now. So d of g of mu, and remember, here we just have one dimension, so I'm using little d, not the del. And what we get is, well, we've already taken this derivative before. We can do it one more time. You take the 2, comes out, cancels with this 2. You're left with this. Then you take the derivative of the inside. That's just -1. So you end up with negative sum I equal to 1 of n to n of zi minus mu. And then the new part is we need to take the derivative of this with respect to mu. But that's pretty easy. You take the square, it comes out, cancels with this 2, and you're just left with this quantity divided by this. And then you take the derivative of the inside, but that's just the derivative of mu, that's just 1. So it turns out to be really nice. So that's just mu minus 160 over sigma squared. And now we're going to want to set this to 0. And we just rearrange a little bit. And so we'll first rewrite this first term as the sum of zi's. Minus gives you plus mu. Mu is summed up n times. That's a constant summed up n times. That's just n times mu. Plus mu over sigma squared, right? I'm just doing this over this, and then I'm going to do minus this over this. Minus 160 over sigma squared. Set that to 0. Now I keep the mu terms on the left-hand side, move these guys to the right-hand side, and I end up with this. Okay. And now, if I just factor out mu and divide the right-hand side by n plus 1 over sigma squared, I get that the final solution for mu, which we will call the map estimate, is equal to, of course, this in the numerator. And the denominator is just n plus 1 over sigma squared. Okay. That's map. That's the map estimate. It looks maybe a little bit complicated, but let's remember some things. One thing is that let me remind you what the maximum likelihood estimate is. And we're just going to get it from this equation by erasing a couple things. MLE was the sample mean, if you remember, for this problem. The sample mean is just the sum of the data points over n. So we just remove this like sigma squared business, and we are left. Oops, we're left with the MLE. That's not right. The MLE estimate. Okay. And so you can see that really the sigma is the only, like these terms are the things that are kind of changing the estimate. And now the natural thing to do is to kind of study the extremes, as you may have seen in this class is a common strategy to understand some mathematical expressions. So let's just take the two extremes of like when sigma squared is really, really large and when sigma squared is really, really small, which remember our mapping was sigma squared really, really small variance. We're extremely confident in our prior. Sigma really large, you basically get something like this. We're extremely not confident in our prior, to the extent where sigma, if it's really, really big, you basically have zero prior at all. There's just almost a uniform distribution. And it turns out that the math is going to reflect this kind of idea as well. So let's just do these cases. So the first case is if, okay, let's make this precise. So if basically we're going to do the case where sigma squared is small. If sigma squared is small, then this is really small, this is really small. So these numbers are really, really big. And so if they're really, really big, then they're going to dominate this and dominate this. So you're just going to get this over this, right? And so formally, what we're going to say is that if 1 over sigma squared is really, really big, so if it's much, and this is how it's written, if it's much, much bigger than this sum I equal to 1 over of n to zi, and 1 over sigma squared is much, much bigger than n. So basically, it's just much bigger than these numbers. So you can forget about them, because these are the dominating terms. Well then, and in other words, just to make it clear, in other words, we're just saying sigma squared is small. Well then what happens? Then this mu map is equal to this over this approximately. So it's approximately equal to 160 over sigma squared over 1 over sigma squared, which is just equal to 160, right? Because this goes up here, and you end up sigma squareds cancel, and you get 160. So in other words, if we have very low variance, which means we're very confident in our prior, right? Remember, this was where you have basically a peak for your prior, like absolutely certain that it's 160. Well, then your map estimate is just going to be 160. It's just going to be exactly what you thought of your prior. This data, and in other words, if the data is not large enough to dominate this prior knowledge, then your estimate is just going to be your prior. And then the alternative is, as you will expect, that if the data does dominate your prior, or sigma is going to be large, so we're going to change sigma small to sigma large, and this is all to be considered relative to the data set size, right? And that means this 1 over sigma squared, if it's large, then 1 over sigma squared is small. And in particular, if it's much smaller than the sum and n, well, then what we end up with is that the map estimate is approximately equal to sigma's large, this is small, so there's basically tiny, tiny, so this and this dominate. So you just end up with I equal 1 to n of zi over n. And that's the MLE estimate. So in other words, if your prior is kind of useless, as in you have no prior, you just end up with the MLE thing, which we saw before, which makes complete sense. It's completely based on data, has nothing to do with any prior knowledge. Okay, so that's, yeah. And the other way to think about this is if you have some sort of prior knowledge, then it is helpful if you don't have much data. But if you end up gathering like a bunch of data, then eventually just wash out your prior, and that is what you can use for your estimate. Okay. And that's all there is to say about that. Now what's left is just to map this to the machine learning setting where we estimate the conditional PDF of y given x and see what we get, and then we'll be done. Oh, and to make this very clear that we're doing exactly the same thing as MLE, except we're going to need to assume a prior on our parameters, let's just go back to this MLE lecture and just copy and paste that in, and see what changed. So in MLE world, we had this. We were like, okay, let me just copy it in, and then we're going to see what's new, or what we add. So exactly the same story. We want to still estimate this. This as only one solution, as most things in computer science, which is you restart the application. All right. So we're back to this, yeah. So we want to estimate the conditional PDF of y given x. So far, let's talk about what we had in MLE. In MLE, you had the data set. Each one of these points, which look like these ZIs, you have n ZIs that are IID. They're these multivariate random variables. They come IID from some distribution. So far, same kind of story, right? And I just mentioned that there's this chain rule property for this kind of joint PDF, which breaks things up into the conditional and to the marginals, which we saw is going to be used in a little bit later. Okay. Then, remember, in all this stuff, you have to assume kind of what is the PDF that's like what's the distribution generating your data, and so we have to make an assumption of what is the distribution of y given x, right? Because we're going to need to estimate this quantity. We want this function, this conditional PDF, to be some parametric function, some function that depends on some parameter, which we're going to be able to optimize over. And so we're going to have to make a choice here, and then choice that we're going to make because people make this, maybe it's reasonable sometimes, is to assume that it's normally distributed. And we'll see what happens. And in particular, we assumed it's normally distributed, and it has to be some function, probably, that depends on x. Like the expected value should probably depend on x. And maybe, yeah, we had this plot, if you remember very briefly. It was like, in the simplest case, maybe the trend is something like this of f base. So this would be like f base, let's say. And so for each x value, you can see that the expected value of y, which would be like these points, which is f base, if you remember, the expected value of y, given x, is clearly changing with x. Okay, so you're going to want this random variable's mean, which is this quantity, to depend on x. And then we said, what function do we pick for that? Well, a natural choice given everything we've been studying, and that seems simple, and we can try working things out nicely the first time around, is just pick a linear function. So that means we can represent any f base that's a line. Fine. And variance 1, which just means that the actual data generating distribution is a normal distribution for each value of x around this mean, with this mean. So it'd be like this. Wow, I'm really bad at drawing these, but something like that. And that just meant that the PDF has this form. Okay. The new thing now is that we need to assume some prior knowledge on what the parameters might be. Okay. And so there's all sorts of choices you can make here, but the one we're going to make is we're going to say, okay, we we just hope that the kind of that the parameters describing this aren't too complicated, okay? And in the case of polynomials, it's even more clear. We're not going to say, we're going to say like, oh, maybe the weights are close to zero. The parameters are close to zero. We don't want it to be like too complicated of a function. We think it's maybe something like a line or whatever. And maybe the features aren't multiplied by too large of a number. And this sort of maps to this idea that we want to select like we have a bias or a prior knowledge towards like simpler predictors. And okay. And that's going to be encoded as follows, which is we're going to assume that these parameters, which are vectors, and we're going to say each one of their indices, so each wj, is normally distributed with mean 0. So we think the parameters are no more likely to be positive or negative and kind of maybe on average 0. And some variance, which normally you'd write like sigma squared, but to make things nice for future, and this only makes sense when we get to it at the end, so I'm going to call this 1 over lambda. And this lambda is going to be exactly the regularization parameter we've seen before. Okay, so this is their variance, and I've only chosen this because in the future it's going to map nicely. And working this out in the forward way, no one would ever pick this and realize that. Okay. So anyways, yeah, and we're going to assume that this is IID, so maybe I write it in this short form, IID. But we're going to, okay, actually this was not a good idea because I wanted to emphasize something. So I'm going to say that these are IID, but only for j equal to 1 up to d. So I'm only going to assume that the weights we think are no more likely, let's say, to be positive or negative and maybe kind of centered around 0 for the parameters indices 1 to d. But remember index 0 parameter, there was this W0 term, that's our bias term. We're going to have no bias towards that, or at least we're not going to have a bias that it's 0. Because remember, we want to kind of allow that to be like any sort of y-intercept, any sort of bias that shifts things up and down. So the assumption for this W0 is often that it's also normally, let's say, distributed with 0 mean, but we're going to make the variance extremely large. So we're going to say it has like some variance sigma squared for a very large sigma squared. And the idea is that this is, okay, when you have a very large sigma squared, that becomes approximately uniform on the interval minus a to a with a very large. And in other words, we just have no kind of bias towards any value of mu naught. We don't want to force it to be closer to 0 because once again, it's this y-intercept, which, I mean, like let's say your house prices are in one case given to you in literally like the numbers are written in like you write out 100,000, like that number, and that's what you're, and in another case, someone gives it to you where everything's already multiplied by like 100,000. So maybe your house prices are like 1, 2, and 3, but they really mean like 1 times 100,000. So you don't want to bias towards any of this scale stuff. Okay. Cool. So that's the setting, and if that all makes sense, all that's left is to work out the math and see what we get. And yeah, let's just quite literally copy and paste the procedure from before and just change things when we needed to plug things in. So up to this point, everything was the same. Almost. We'll make a couple minor changes. And this is really to emphasize that the procedure is like standard until you need to plug in your PDFs or PMFs that you've made the assumptions about. Okay, so now our parameter is not mu, right? Our parameter is W hat. W vector is the parameter vector we're trying to find. There's some true parameter, right? W star. That's generating data. That's like this F base thing. We're trying to find that W star. And So the procedure goes as we've seen. So we're going to search over parameters W that maximize the likelihood times the prior we have on W. Okay. Now we're going to rewrite this as this product of, well, the product of these zi's. The zi's were like yi, xi. Or xi vector yi. This is W, this is W. Right? And after that, we took the negative log likelihood, and then we had this log, yeah, okay, and then all that's, I just need to change the terms in here again. This is W, and this is W. Okay, so you should see that everything is quite literally the same, except with renaming variable names. And, okay, this step is also still, as I said, the same. Okay. And so you might remember in maximum likelihood, we had encountered the same quantity, this log of this thing. And then we took this thing and we used the chain rule and expanded it like this. Then we plugged in this quantity as the normal distribution's PDF, expanded the log into all this, and did all this simplification. And maybe I can even remind you how that worked. If you look over here, we were doing this MLE stuff. We got to this quantity. It looks exactly the same as what we have seen. It's the sum of these logs of xi, yi. Then what we did is we applied the negative, but then we changed this using the chain rule as follows, right? You get the conditional times the marginal. That's the chain rule if you have a joint. And then we did a bunch of steps, which is like this log splits this product into things, and then so on and so on and so on. And the point is, you get to an inner expression like this. So we're just going to take that for granted that we've already done that and plug that in, which is similar to the people's height example we were working on. And then it's going to just be left to expand out the extra log term over the parameters. Okay, so that quantity is the sum. Yeah, and so as before, the sum is only going to apply to this quantity here. So this log term will have nothing to do with the sum. And so that quantity, which we worked out before, is going to be the sum of yi minus xi vector transpose w squared over 2 minus. And why is it minus? Because this minus is going to be expanded into here, which canceled out the minus of this normal distribution. And now this minus goes here, and we erase this minus. Okay. So you can work that out in more detail at home or double check that that makes sense. And now we do the same procedure as we did before with people's height. We're just going to expand this out to see what it looks like. And we do that in blue. Then we're going to plug it in and be done. Okay. Okay. There's another assumption that I slightly forgot to mention, which is we also assume that this W, okay, let's, like basically this is complicated. This is a joint PDF of these W's. There's D plus one of them. We'd really like to write them like this. Okay, let's write it. So I'll explain to you why there's another assumption that's made, because otherwise the math gets ugly. So this is what this thing looks like, right? And really what I want to do is I want to say this. I want to say, okay, this would be really nice if this thing was not this giant joint thing, which I don't know what it is, but if it was just equal to P of, let's say, W naught times P of W1, all product up to P of WD. And when can you do this? You can do this when things are independent of each other, right? Independence allows you to write this product. And if they're identically distributed, these P's are all the same. And here maybe I can emphasize one thing which, yeah, okay, we're just gonna have to take from context that this P is the P for W naught, while this P is the P for W1 up to WD, and based on this assumption, the distributions of Wj from 1 to D is clearly different than the distribution of W naught. Okay. To allow this product thing, we need independence. We have independence of these for J. We don't have that W naught is independent of these. So we also make the assumption that W naught is independent of all the others. And so I guess I'll make a little bit of space. And so the other assumption is that W naught, whatever, and independent of Wj for J in 1 up to D. Okay, that independence allows this product structure. Okay, and now we can plug in what are all these P's. And in particular, we will get that log, this first distribution, this first PDF is different, right? It's this one that's basically a uniform. So that's going to be log of P of W naught. But then all the others are the same. And so we can write them as a product from J equal 1 till D of P of Wj. Okay. And then the log of two products, sum of logs. Okay. This log of products, I'm just going to do it in this step, becomes the sum. Okay, maybe one more step. Becomes the sum of logs, right? And so this product changes to sum, J equal to 1 of D of log of this. And then we can finally plug in what this is to get that this quantity with it plugged in, well, it's going to be, so we know Wj is normally distributed like this. So just to save some time, I'm going to take this thing and change some terms in it to match. So it's like this. It's going to look of this form. But the things that are different is zero mean. So that means this quantity is minus 0, minus 0. It has a variance that's not 1, so you get a sigma squared. And remember, it's not sigma squared. We chose 1 over lambda. Okay. And now that whole thing's in the log. We do the same procedure as before, which the log of this thing becomes the sum of logs. Log is going to cancel with the exponential. And we end up with the following final expression. Okay. And maybe I went a little bit quickly so that we can get to the end of this. But I'm sure you can trust me that you can work this out at home. Okay. So you end up with an expression that looks like, so this sum times this thing, you're going to get just D times the log of this. So, okay. D log of this. And then the guy out here, this exponential canceled with the log. You still have the negative. The sum was still there. So we end up with negative sum J equal 1 to D of this expression, which is just y squared And maybe I'll write there's a lambda, which was in the denominator, but it was 1 over lambda in the denominator, so you get a lambda out here, and then you get 2. Okay. Great. And so now we finally have this expression. And so we're going to take this expression and plug it in here. And to save on some space, because it's not going to fit in the same line, we're only going to take the terms that depend on W, because that's all we're minimizing over. Any constants there, they're not going to affect it. So this quantity doesn't depend on W. We can forget about it. This quantity, okay, it depends on W, but we've chosen the variance to be extremely large. And so we're just going to assume that basically this is just the same number for the whole time. Like this was the assumption, which is it's basically a uniform distribution. If you remember, a uniform is just the same number. So that's this kind of assumption. So that's, we're just going to say is not going to affect that optimization either. And so we're just left with this to plug in. So let's just do that. Replace that with, and now remember there was the minus log of P of W, but log of P of W has the minus here as well, so the minuses cancel. So you get plus lambda sum j equal to 1 d of y squared over 2. Okay. And yeah, and this is we're in really good shape now, because if you kind of squint at this, first of all, you'll notice that this is yi. There was a big mistake, which is, right, this parameter in here is supposed to be the parameter with which this PDF is with respect to. So this is not y, it's wj throughout everywhere, obviously. And this j is indexing this thing. So this is wj, this is wj, this is wj. And now if you look, this looks very much like the regularization term. This looks like the normal squared loss we've had before. And what we can observe is if we take this quantity and just slightly add some extra constants and so on, first maybe rearrange this loss to look like what we've seen before. Since it's squared, it doesn't matter if you do something minus the other. If you then notice that in our empirical risk, we had this like 1 over n out front. Well, we can multiply the whole thing by 1 over n. So 1 over n times this. That looks like our empirical risk. We multiply the lambda also by 1 over n. And now we get exactly that this is equal to the usual L hat of W. And this is the squared regularizer. And all that being said, we end up with that this whole thing is the same as minimizing L, what we called L lambda, which is the regularized empirical risk of W. Okay. And putting that all together, what we end up with is that at the end of the day, we wanted a predictor, which is going to be this estimate of F Bayes. And maybe let me just make this absolutely clear how related this is. So in MLE, we also got to this point at the end where we found out the minimizer is just the minimizer of the empirical risk, and we knew the solution for that, and so on. And then we followed this procedure for F Bayes. And I'm just going to copy and paste it and show you exactly how similar this is now. So we want to estimate F Bayes using our estimate of the PDF. So F Bayes is defined as this. When you expand the expected value, you get this. It's equal to this thing. Or we want an estimate of this thing. We got one. Instead of W star, we estimated with W, not MLE now, but W map. That's all that's changed. We've chosen a different way to estimate it. Estimate the parameter describing the conditional PDF. And what we end up with is a new random variable, or sorry, like we can treat this as a different expectation, the expectation of some new random variable y prime, where y prime is distributed normally with not WMLE here, but W map, which we have solved for. And so finally, we say that our estimate of the F base is going to just equal to, right? We look here, what's the expected value of this new random variable? Well, it's exactly this quantity inside, which is just this linear function, which is this. And this W map is exactly equal to this kind of like F hat lambda we've seen before, where F hat lambda minimizes the regularized empirical risk. And so it turns out that you can think of this regularization thing as doing this MLE thing, but with some prior knowledge on the parameter. And the prior knowledge on the parameter is in terms of a normal distribution that has variance equal to 1 over lambda, right? And now we can think about this. So when is the variance large? The variance is large when lambda is really small, right? And when lambda is really small, that means large variance, which means we have basically no prior knowledge on our parameters. We say they can be anything. In other words, that would mean like we don't penalize large parameters because we really don't know if they should be large. And what would it mean not to penalize? That would mean that we make lambda really small. That's a small penalty. And that's exactly what maps here, right? Small lambda, large variance, no prior knowledge, we don't penalize at all. And then the other direction is, let's say we really do not think the parameters should be large. They really should be tiny, tiny. We think it's very uncomplicated, the predictor. Well, then we'd be like, okay, variance is tiny. How do you make variance tiny? Make lambda really large. Lambda really large, if you remember in regularization, is a very large penalty. Remember this very large penalty. So we do not want the weights to be large. And that's the kind of mapping, the nice mapping you have between these two views of things. Okay, and then the one last point I want to make is that if you instead of all this had changed your prior assumption to not be a normal distribution, and this will be called, this above thing was called ridge regression, if you remember, when you have the squared penalty on the weights. And there's this thing called lasso regression, which is we have a different penalty on the weights. That was the absolute value. And that, it turns out that you can get that back if you make a different assumption, different prior knowledge on the weights. And that is that your weights or your parameters, Wj, are not distributed normally, but instead distributed as a Laplace random variable with mean 0 and what is called deviation or something. I forgot what this term is called, but it's not the variance, if I recall. It's some other term. Or maybe it's called the scale. I think it's called maybe the scale parameter. But anyways, you make that parameter in the Laplace, which is one of its parameters, 1 over lambda. And it's the same story that their IID for J in 1 to D. You make the assumption that W naught is Laplace 0 with sigma, let's say, well, here you call it B instead of sigma squared for large B or very large B. And then you also assume an independent for J D. And then you do the same procedure. And what you will find is that this W map for this procedure now with this Laplace assumption is going to equal to, you can imagine the same exact thing basically. It's going to be the minimizer of this type of thing. Of course, the first term is going to be the same because this has nothing to do with the assumption on the prior, on the parameters. And this term is just going to change too. And what's it going to change to? Well, it's almost super obvious when you write out the Laplace distribution. So the Laplace distribution looks like this. Or the PDF, sorry. It looks like this. It's almost the same as the normal one, except this thing over here, and I should write that this is the assumption on Wj. Remember on Wj we had this kind of assumption, which was that Yeah. Okay. It was zero mean. And this was the version for the normal distribution. Well, for the Laplace, it just is changed to this. That's the definition of its PDF, if I recall. This might not be 2. I can't remember for sure, but take that with a grain of salt. But then it's obvious. If the squared thing appeared here because of the squared, what's going to appear there? It's going to be the absolute value. So you almost don't even... The math's exactly the same story. And this penalizes the weights a little bit less from being large because it doesn't square large weights. It just takes their absolute value. And that causes for some like other behavior. But you can think of it as having a different kind of prior on the weights. And if you remember, the Laplace distribution looks more like this, while the normal was more like spread out. Okay. And that's called lasso regression. You can make other priors and get other type of things and so on. And I guess the last 25 minutes, we should probably get to the whole midterm review stuff. But is there any questions about this while I move to that? Okay. Let me just do one thing. Okay, good. Yeah, so midterm review. So as I said, the midterm is really going to focus on the stuff after midterm 1, which is kind of when we got into optimization and evaluating our models and then this MLE map stuff. So that's really going to be the focus of things. And I put the formula sheet up so you can see which equations you have available to you. If you think that something should be on there, but it's not, it's very likely that on the midterm, you will just get that equation given to you in the question. Like there shouldn't be much you need to remember. Okay, in terms of equations. Oh yeah, it all started with how do we optimize things? Right, what's the story? We just want to do ERM. And to do ERM, we need to do this like optimization. Well, we talked about the estimation thing before the midterm, but we want to do this optimization. So that was like a large focus of things. And one simplifying thing was like, well, let's study it when we're in the regression setting specifically, and when we have the sample mean estimate of things, and when our function class is linear, and we called this the linear regression setting because we use linear function class. And the whole procedure was just, how do you minimize this? And the realization was, yes, if we make this function class parameterized by something, such as linear, like we describe them as linear functions, where every function has a one-to-one map of some parameter, then it turns out that minimizing such a quantity is the same as minimizing this function where you plug in the predictor inside and minimize over its parameter. And we found with the closed form solution that this f hat here is just equal to this, like, I mean, it's obviously a linear function with this as the closed form solution. And there was like all we did was took the derivative and set it to 0 and solved the system of equations. And you can like review that to some extent. You obviously will not be asked to solve this giant system of equations and things like this. At most, you're going to be asked something with 2 variables. Okay. But you should understand that like the procedure is that you take the derivative, set things to 0, and then have to solve for that vector. And in pseudocode, it was as simple as this. You have a learner which takes in a data set, just calculates the corresponding quantities you need to solve for W, solves it, and then outputs the predictor. And that's it. And visually, it's to be thought of as it's finding the line that makes the squared errors between all of these data points, this is your data set, the smallest possible. That's it. And then gradient descent was this procedure that doesn't give you the closed form solution, and it's this iterative procedure which addresses kind of 2 things, which is we're going to see the computational cost of the closed form solution might be higher. And the other thing is that for various problems, there might not even exist a closed form solution, which we're going to see in classification after the midterm 2. And one of the questions online was, will the midterm cover the content of today's lecture? And the answer is yes. It's going to cover all the MLE and map stuff. And as I said, you can expect I think you saw this on your assignments, but the questions are going to be, change the prior on your parameters for the map, for instance, case, or even for even outside of machine learning thing, like when you had people's height, maybe I'll tell you, oh, let's say you had a Laplace prior instead, or maybe we had the normal distribution, but now I tell you the variance is unknown, but the mean is 1 or something. Things like this. So, and you just do the same procedure, but there is some slight changes in the equations, and that's it. Okay, and so there was this gradient descent stuff. So there was 2 versions of gradient descent. There was the second order gradient descent, which was somehow better than the version of first order gradient descent. Because it had, all I'm going to say is it had this, what is called the gradient update rule with kind of a correct step size, which is scaled appropriately related to the second derivative. And if you just do this iterative operation with this corresponding second derivative as the step size, you will approach W star as t goes to infinity. Yeah. But unfortunately, the second order gradient descent, calculating the second derivative, can be very expensive for multivariate cases. So we just approximated with some number and replace it with just a constant, a step size, just a single number at each time step, called the step size. And that's the first order gradient, or we just call this gradient descent update. And in the multivariate setting, it was the exact same kind of update, except you just take basically the partial derivatives in each dimension, and you replace this term with the gradient. Above it was just the derivative. And it's literally, you're updating the weights per dimension, right? There's no kind of intertwining between dimensions. You just take the partial derivatives, and that partial derivative is the only thing that affects the update of the weight at index 1. And the same for those. Okay. That was your idea of gradient descent, and there was different step sizes, and the whole idea of these different step sizes was that you're somehow trying to get kind of the right sort of maybe estimate to 1 over the second derivative. And yeah, there's various ideas. This is not on your formula sheet, but you also don't need to remember it. It'll be told in the question, and it can ask you about, I don't know, various things of what happens to this step size as t increases? Does it decrease or increase? And why might that be a good idea, which is slightly described in the PDF version of the notes and stuff like this. Okay, and then when we got to the machine learning setting, the actual algorithm for this gradient descent stuff was called batch gradient descent, which is you calculate the gradient of the empirical risk. And since the empirical risk uses all the data, that's called the batch version. It works with the whole batch of data. And that had a closed form solution like this, which once again, you don't need to remember. It will be given in the question, this type of thing, which was just you might need to calculate this again. I don't know. It wasn't too hard. It was you just take the derivative of some multivariate function. But that's what the gradient was, right? The gradient was this thing. And the corresponding algorithm was now this iterative algorithm, which took in a data set, but also took in an extra parameter called the step size and the number of epochs you run for. And if we want it to be completely formal, we should technically say that now our learner doesn't only take in as input a data set, but it technically is also takes as input a step size and a number of epochs, or people will say that these are extra parameters passed to the learner, they're hyperparameters passed to the learner, and so on. Because notice this is a bigger input than we previously talked about. And if you change each one of these, you get a different learner, right? This is the whole evaluating different learners. You really do get a different learning algorithm. And the procedure was that you randomly initialize a set of weights. You could just set it to all zeros. We didn't talk much about that. There's a whole literature on how to initialize. But the idea was that you run this iterative process of taking gradients and updating your weights over and over again. And if the step size was chosen appropriately, then this should converge or get closer and closer to the closed form solution. And the visual that you should keep in mind is that at the beginning, it's very poor. This is the 0th step parameter. And as you take more and more gradient steps with good step sizes, you will get closer and closer to the closed form solution, which is the purple line. And then there was a discussion on computation, and like, I guess roughly speaking, you should be familiar with how to just, look at an equation like a sum or a vector multiply and understand how much computation it's going to take. Like multiplying two vectors takes the computation of the size of the vectors. The sum is just a for loop, so you just count the number of things you're summing over. Things like this. You can be asked like a question or two about how much computation does it take to do some sort of procedure. Maybe you tweak the algorithm some small way. Does things change? But yeah, we did this calculation. We found the closed form solution scales the number of computation steps, scales as data set size, and these parameters, or sorry, the dimension of your features or weights parameters. And we saw that for batch gradient descent, the formula looked like this. And then the comparison we made was that, well, if t is less than d, then t is less than d, then this quantity is less than d squared. And so batch gradient descent will be more efficient in this case. And for various problems, well, this would be some, like, if you were given these two things and then you're asked like, oh, if t is, let's say you did 10 steps of batch gradient descent and you did, and d was like 1,000 or something, which one is more computationally efficient? Then you should understand that batch gradient descent would be more computationally efficient. Yeah, and then there's mini batch gradient descent, which just was batch gradient descent, but you broke up the data set into mini batches. Like this, length b. And we said the number of mini batches is just the smallest. You round down to the nearest integer. It's the floor of n over b if things don't divide. And we just discard the last n minus m times b data points. And that was just for notational convenience, because everywhere you'd have to have this extra if statement checking if things divide, and then you end up only kind of getting a little bit extra data. But in practice, you will end up using all of it. And maybe on your assignment in the homework, I don't know. But you can imagine being asked things like, what happens if we actually use the last thing? How would the code change? Would it change at all? And things like this. Okay. And yeah, the thing that changed was now our empirical risk is like this empirical risk only for a mini batch. So you should be, I guess, comfortable with how this indexing worked, which it only took like a subset of the data, which is of length b at particular indices. And this would be the mth mini batch. And the gradient descent algorithm for mini batch gradient descent, same story. Now you have a mini batch parameter, and you have an extra loop, which now does gradient steps over smaller batches of data, these mini batches. And so that's why you have this extra inner loop. And there was these observations that if the batch size is all of the data, then you return to batch gradient descent. If the batch size is of size 1, you end up with doing like steps with only a single data point for your estimates, and you end up with n steps inside the inner loop. And this was called stochastic gradient descent. You definitely don't need to remember like names like this, I think. Okay. And then, okay, we did all that, and then we said, okay, let's increase the function class to be more powerful. And one way to do that was to make it of polynomials instead of linear functions. And the procedure there was just to have this polynomial function which takes in original features and maps it to some bigger space. The dimension was given by this formula here. And the function class looked as before, except the only thing that changed is you map your original features using this phi of p function. Notice that you still have a function from original features to labels. It's just internally it does this extra mapping. And the critical observation was that these function classes are strictly bigger than before. So if you have second degree polynomials or less, it has functions that first degree polynomials or less did not. In particular, it has like a parabola, which lines you can't draw with a line. And this means that when you do this optimization, when you're minimizing in empirical risk minimization, you have more functions to pick from, which means you might be able to find something that minimizes your empirical risk more. You get a smaller minimum. And so the observation was, well, the empirical risk, as you pick these are the closed form solutions, the true minimizers, the empirical risk will only go down as the function class size increases. And visually, that was like, if you start with lines, maybe you can't fit the data well. Parabolas, maybe I can fit it better. Higher order polynomial, I can fit it like super, super well. So I can get that empirical risk to go to approximately 0 if I have P to be very large, roughly speaking. There is, of course, some issues. Maybe this is a good point to know, is like you can imagine in the, for instance, regression setting, even for the same X value, like a house of, let's say, 3 rooms, that's not a 3 rooms, you can have multiple different prices. So you can't always drive it down to 0 because there could just be multiple labels for the same X. Okay. And then we moved on, how do you pick like your, how do you pick basically the learner to use, the model, the kind of the function class to use? Because maybe in some way you should think of it as like you're the algorithm designer, you're the guy, the person that's designing the learning algorithm, and what you're presented with is like someone that's already gathered data. Maybe it's like the whole internet or things like this, and you kind of think like you don't really have too much power in how much data you have, what the data looks like what are the features. And so really you are just there, like all you can do is tweak the actual learner. And really that means if we're doing empirical risk minimization, it's like, do I use mini batch or batch gradient descent? How do I tweak? And another big question is, which function class do I pick? And so this is, yeah. And so that was kind of the discussion of this section, which roughly speaking was the following observation, which is at the end of the day, we want to minimize the actual, we want to minimize the actual risk, but we have been looking at this empirical risk. And the observation is, well, if F, if we can make F big enough that it contains an F or like F base that makes this empirical risk small, then we're good. However, we're like kind of in conflict with this fact that making the F really big maybe makes the empirical risk estimate not as good. Or in other words, what I guess is, when would ERM work well? Well, it works well when your function class really does contain a good function for labeling the data, and the empirical risk is a good estimate. And these are the two kind of competing factors of trying to achieve both of these, unfortunately, are competing with each other. And okay, we went over these various details, but the idea is that we broke it up into these errors, one being an error in the irreducible error. It's like the best you can do. There's nothing you can do about it. It's due to just the inherent noise of the features you picked. Then this is the error due to the function class not being kind of representative enough. And this is the error of not having enough data, maybe, or the function class being too representative that it causes your empirical risk to not be a good estimate. And so these two competing factors, okay, you should be familiar with these things for sure. If I what are these errors from? I'm maybe not going to go over it. It's like you can just read it. We've seen it a million times, but you should be familiar with how to decrease it if you can, what affects what, and so on. And you should also be familiar with this kind of plot, which is like you should be able to know what's the estimation error, what's the approximation error. Well, you just look at the corresponding quantities. In your formula sheet, you have this equation. So it's quite a manual procedure if you want it to be. You just kind of look at where is this plot, where is this plot. Okay, that's the black line, that's the green line. Well, this thing at this value is the approximation error. That's just this equation. But once again, the kind of the purpose of all this was that there's a trade-off between these two things, which is as you increase function class size, approximation error goes from very big to very, very small, like here. However, the estimation error goes from very, very small to very, very big. And usually there's some sweet spot, some good point, the point you want to pick somewhere in the middle. Okay, and these things were all like kind of theoretical up to here. And so then we said, okay, how do we actually do this? Well, the idea was you use you have a data set, and we're going to use the original kind of data set, or like this, we're going to pick a large chunk of it to be the training set, which we're going to use to actually, train train on and have our learner work on. That's the training set. And then we want some like unbiased set of data that has never been used to optimize over or anything like that, to estimate how it's actually doing on new data, because we really want this orange curve. And we want this orange curve is like a description of how well are we doing on new data. And we have a bunch of different learners. They vary due to different things, like the function class size or maybe the regularization parameter. And we somehow want a good estimate of how they're doing on new data. So that was this idea of breaking up your data into train and test. And yeah, rough idea, like make the test set bigger, you get a better estimate of how you're doing on new data, but then you have less data to train on, which might cause you to overfit more. And there's like these kind of trade-offs that you should have some high-level intuition about. And the story is the same, except this orange line can be kind of more like less smooth in practice. Okay, and then there was this idea of this bias variance trade-off, which was just another way to decompose your error. Instead of comparing to f star, which is the best function in your function class, you compare it to the average predictor or the expected predictor. And the effects were similar to this kind of approximation estimation error. Bias goes down if function class goes up, right? Our average predictor can get closer to f Bayes, and then the variance has the opposite kind of effect. Okay, and then there was regularization, which was like kind of a smooth way to introduce more complicated or less complicated functions, which is this idea that large weights means more complicated functions. So if we want kind of like some like loosened version of making the function class less complex, we would just have a large penalty. And a small penalty kind of means you allow for more complex functions, so you have bigger function class. And there the plots were also of a similar nature, except it's kind of the inverse dependence on lambda compared to p, which was the polynomial degree, which is if you basically have lambda equals 0, that means you don't penalize weights at all. That means you have very complex functions are allowed, and you can have very high variance, which is this area here. And otherwise, when lambda is really large, you basically say, I want all of my weights to be 0, which means you're kind of restricting yourself to very simple looking functions. And so you probably can't represent f Bayes, but your functions probably don't vary that much if you change the data set, so low variance. You'll definitely be asked all sorts of questions about related to plots and stuff. And then, yeah, all that's changed is your empirical risk has changed to this regularized version, and you just solve this minimization problem. I said that you can solve it in a closed form, but we never worked that out. Maybe you can imagine on the midterm working out the closed form solution, but maybe when d is like equal to 1 or something, and see what happens. Maybe you already did it on the assignment, I don't remember. But you should be familiar with, at the end of the day, it's just a function you're trying to minimize, and you have two procedures, which is set the derivative to 0 or do gradient descent style thing. Do an iterative method. Okay. And then maybe the last minute is like, all that was left was this MLE and map stuff, which we have just covered the last couple days. It's like, you can imagine the procedure is going to be like maybe changing the assumptions on the PDFs that we've seen in class and working things out and seeing what you get, those style of questions. And this idea of knowing like what this prior knowledge means in map is useful too. The discussion of like, if you have a stronger prior, then it biases you, or like it's more likely that your estimate is closer to your prior knowledge versus the other way around. Okay, well that's, I think, everything. You have the whole reading week to ask questions on Piazza. There still is, the TAs will still have office hours if you want to come to those. And otherwise, good luck.